yourself familiarized with design process, and also get yourself prepared if you are coming to automation space. So I may be skipping some process so that the video will not be so long. Okay, so but what I want you to do now is for you to um, share this particular video and like it, and also comment. Okay, when you see the video, you comment. So this is why Facebook we now said, okay, whenever a subsequent post is coming available, okay, let me send this information to this person because it's of a greater importance to him. But if you don't like, if you don't click like, if you don't share, if you don't comment, subsequent video similar to this shouldn't come to you for you to look at it. All right. And this particular design will take up to 3 chapters. Okay, you should get part one, part two, part three, because if you want to do all of them in one video, it will be so voluminous. So the megabyte is going to be heavy for you to upload. So we're going to segment it into 3 parts. Part one is for us to design. Then part two probably will now take you to, like I told you about schematic. We're going to design it with the hardware, using hardware. Okay, because that is why the where I normally advise my students, also my followers, that you must familiarize yourself with design concept and your design skill. All right, so now let's go now. This is my network one. According to them, they say we should put a lashing. So I put first instruction, that is my start instruction, and this is my stop instruction. Then this is my internal bit memory. So you come again, you put my lashing, this is my bit for lashing. Okay, I'm done with the instruction here. So let's bring up the narrative. First of all, let's put up our tag. So we're going to call this one a process, start process. Let's say start process. Okay, I have already filled in their tag's name. Okay, so this one is going to be inputted to I0.0 in our CPU, in our PSC. So the tag, the bit registrar is going to accept this one from I0.0. That is the tag address. Okay, what I mean is that this particular logic is going to be connection process is going to be terminated on the address of I0.0. That is the bit tag number. Then this is my stop process. I'm going to stop it with this. So I start the process here, I stop the process here. Then this is my internal bit. Okay, it's going to be my internal bit. So let's say if I have the name to give this can be start logic or lash logic. Let's say, let me get my narrative. Narrative said is going to be activated and lashed. So I'm using this now to activate the logic, and I'll lash it with this. So you're going to be lashed logic as well. I'm done with this. Okay. If you understand, um, if you're not familiar with logic principles, you will be confused. But just follow the voice and follow the process. Okay. By the time you register the course, you understand it better. We have a lot of exercises. Okay. If I train you with this only 1 week, you'll be working on your own. I'm telling you the truth. If you come and register this program and they work with me for just 1 week, you'll be able to write simple programs and simulate them. And you also understand their operation sequence, all right? Now, this one said we should put the conveyor in energize mode and they lash the conveyor. Now, this particular logic here is what we call lashing logic. Whenever I want to put up a design, it's always advisable to create your starting point first. Then you start adding other processes from your starting point. Okay, this is the simplest way of writing a code with a lashing logic. Now, we also have, okay, just listen to this voice note. The major reason why I always advise you to understand design, to have design skill first. before going into automation space is because we have more than 1 million people that uses different method to write code. For instance, this network one now, this logic I just put up now, we have more than 10 different method of putting up this lashing logic. Yes, let me show you another way. Just minimize this. There is one other bit called flip-flop. Let me get it now. Let me just put it here, then later I will take it away. Look at this instruction. This instruction, when you get to understand the operation sequence of bit, logic bit, you can also use this to design this particular. Okay, let me put it this other network. Sorry. All right. Now take a look. This one is a flip-flop logic. This instruction requires three signal. Signal from S, that is put it on set. Signal from R, that is to reset it. You set it from here, you reset it from here. Whichever function that you require here will give you output here. That is what I have here. So take away this. Let me show you. Now, when I initiate process from here, this one will get energized and latched here. So in that case, here we put the system, we put this bit on, and this bit will latch here. Beautiful. The same way, I can use this only to generate what I have here. I set this bit on, I get output. If I want to shut it down, I shut down by energizing reset to knock off my output. So this block only give me this, the entire, this 1, 2, 3, 4, this 4 bits that I just used to put up lashing instruction is what this will accomplish. Only this block will accomplish the whole of this 4-bit function. 1, 2, 3, 4 bit. I use them to bring up lashing instruction. Now, the same lashing instruction will be accomplished for using this only this singular block. Okay, so that is the reason why I said you must understand design. If you don't understand design, by the time I write this program this way and I change it by using this block, you'll be confused. And there is another logic I will put up. I will use this method. I will not also use this method. I will use a different method, but the end result remains that I'm going to energize this bit. I'm going to activate this bit, put it on set, put it on position. Okay. So we have more than 10 ways of putting up each network. I repeat again, we have more than 10 methods of writing each network. So different programmer with different skill set of writing program. And what we are looking at when writing program is the most efficient method is what we are looking for. The most efficient and the most fastest and the most precise method of doing that. If your CPU processes your program faster, so that is a good programmer. If you write a program and your CPU find it difficult to scan it, okay, that is the time to scan will take time. So you are not a good programmer. A good programmer should write a program such that CPU should process every bit of your instruction without stress, without wasting time, okay, without booting. CPU should be scanning your coding in a milliseconds, very fast. So the more you accumulate instruction in order to accomplish a particular purpose, the more your CPU and your PLC pass under stress while scanning your instruction, your logic. All right. I give you another example. I have another network here for my conveyor. Okay. But let me just put up another network here. Now, the instruction said we should put on the process and also activate a conveyor. So I want to put up a conveyor. This is a conveyor. Now, this is a conveyor. So I'll put this one conveyor system, maybe I'll say main conveyor. Then the name of this is my main conveyor. This is my internal bit, it's not a conveyor. Look at it, M0.0. Okay. We are using this internal bit to reduce the termination process of your logic. Like to reduce your output, they're going to terminate on your CPU terminals, your CPU input card, your input, your IO card, your input and output card of your CPU to reduce the termination, the hardware that you're going to use. So CPU has a lot of software instructions that you will use to reduce your termination process of your output. And of course, you know that the essence of PLC is to reduce the hardware connectivity in our control panel. That is why the PLC has come to reduce the stress of passing under a lot of connections and troubleshooting that is normally been going on within a control system. So we use PLC to drastically reduce the use of hardware physical components. Okay, so because of that, you should now utilize the opportunity of working with internal instructions, internal bit instructions. Utilize them better so that your output will reduce. Your physical output that is going to be connected to your uh, live operation software hardwares will be reduced. Now, this instruction has been able to accomplish this particular instruction without any connection, any physical connection. So I use the whole of this as my internal bit. The only what I have here as a physical connection is these two, start and stop. Start and stop is the physical input device that I need. This one and this one, they are all internal bit instruction that I use. The same way here, here is going to be internal bit. Okay, the reason is this: once I activate this one will get set, this one will get energized. Now, when this one is energized, the auxiliary bit of this is what I have here. So this one is going to be a continuation of this signal. So this signal flow and come here, still flow back and come here. So this one and this one, they are integral part instruction. Okay, that means if this one is not energized, I shouldn't have output on my conveyor, because until this one is energized, the bit continuation auxiliary will be energized as well before the instruction passes to conveyor to come on. Take note of this, okay? Now, this instruction is complete, but from our narrative, let me show you. Now, from this narrative, the second network said that is going to be the one responsible for temporarily disabling this conveyor. Okay, when the number of set or number of dozen is completed. So network 2 is going to be responsible for shutting down this on temporary and also activating timer. So because of that now, we are going to do something this. So in that case, I'm going to control this conveyor with this network 2. So network 2 is going to cut off conveyor for me. So because of that now, what I'll do, I will insert a contact here, and this contact is going to be C1. It's going to be my counter. Come back with my narrative again. There's a counter on this second network. There's a counter. Okay. When this counter is completed, it will temporarily, let me read it. Product counter sensor start counting immediately when an item is detected. And when the number of each set a dozen is completed, then counter will temporarily shut down conveyor and activate timer. So what is the means that counter we use to shut down conveyor? Here is the means. So counter will shut down this using this means, using this bit. So that is why this one is going to interface between where the power is coming from and where the power is going to. The signal is coming from here to feed here. So I'm going to interrupt the signal halfway by inserting this bit so that this bit can cut off signal from here and also connect the signal back to this place. So that is the essence of this. Now, I'm able to accomplish this. If I simulate this, it will work. If I simulate this now, it will work. Let's do that. Let's just simulate. No, let's finish. So now, watch. I have this network here, and I also have this network here. Now, if I want this network merged together with this network to reduce the expand of my network and to reduce the complexity of my logic for this CPU to scan. So what I'll do is this. I'm going to create a branch here so that I take this one and merge to this network. I'll create a branch here and also bring this my bit, put it here, and that is this bit. Also insert this bit, the same network. I put it there. Then finally, I now put my conveyor being this. So we are done. So this network has been accomplished by this instruction and this instruction combined in one network. So let's do away with this. Okay. All right. Like I said before, we are going to write simple network system, simple logic operation system. Okay. So we're going to make it as trivial as possible. So remember, this one is this, the same set logic, the same M0.0. Then I have my counter here, C1. Then finally, I have my main conveyor. We are good to go. This network is set. Now, another instruction said there's going to be a counter. So we need a counter that will count and break this logic halfway here. So how do we get the counter? Two ways to get the counter. Come to this place. Now, we use this conveyor to send power to the counter. Okay, that is method one. All right, pay attention, please. All right, now pay attention to this other second network. Okay, now second network is this. Take away this. Okay, okay, now this second network. Now, if I want to start this logic, two things are involved. Either I will use this bit, this memory bit, to continue this so that once I initiate this command, this one will be activated as well. So all my starting network can be activated, can be getting ready by this logic, by this latch the logic, this internal memory. Either I use it or I use conveyor. So whichever one you choose, both of them have the advantage and disadvantage. Advantage of using this one is because sometimes when you set this network using this memory to set this one, if peradventure something malfunction on this network, on this logic, okay, it can have different results. Okay, you may have different results if you use this. If you use this internal memory to latch this, then the network will get ready pending when other instructions will commence. But if that is done, if I have my beginning of the network initiated by this bit, if every other logic within this network go wrong, the logic might react differently. But if I use the conveyor, it's going to be a continuation sequence. Continuation sequence in the sense that when this conveyor is not activated, the rest of my logic shouldn't get activation. Okay, they are both okay, but depending on which one is more simple and easy for you to understand. Okay, all right, but now I'm going to use this. So I'm going to bring my conveyor to initiate the command. So if conveyor is set, this one should also be set. All right, so if that is done, so I'm going to also get that counter we are talking about, the counter. Okay, the counter device that will count the product from our instruction. Okay, so come back here, uh, onto our counter bit. So we need counter count up. So it should be count down. Let's use countdown. We're going to count down the value. Okay, all right. So now this is my counter, going to be C. Let's say C1. Let's call it a C1, the first counter. That is why I say C1. C stand for the counter. Then I have the output from the counter. Okay, the output you can say, because it's counting, it's controlling, let's say quality control. That is the name of this counter. Okay, quality control. This counter can be used to activate, this particular bit can be used to activate a particular device that will also register the number of items, so that you see the display. The display will be showing that number of so item is showing on the screen, on LCD device. Okay, all right. So then we're going to introduce that sensor that will be sending the counting to this. This counter is just a registering memory. It's a registering memory. It's not a physical device. So it cannot be fine. It's not a physical hardware device you can feel. So now we need hardware device that will send the instruction to this. Okay, and that should be sensor. So we should put it here. Now put main conveyor first. Main conveyor give us permission to energize our counter. Now, what is this? This is going to be the counter. So, what is the name we can give our counter? We can now say counter sensor or product counting sensor. Okay, let's say product counting sensor, and it's going to be M0. Just type, I think we have it here, product counting sensor, or just say M0.4. Should be there. So this our, no, this total product is not total product. We need let's say product, the name to give that, we should have it here, total product count. Um, I'm coming zero, I'm 0.3. Let's see if it is 3 or going to be 2. No, we need M0.4. Total product count. No, it shouldn't be this sensor. M0.2. The sequence, yeah, let's say sequence repeat. Okay, let's say maybe that is it. No, I will change this name. Okay, so but this is a sensor. Okay, this is a sensor sending instruction to this. Okay, I will change the name, but let's leave it for this. Let's leave this name for now. So this is what we need for the counter. Okay, so we need next we need to load. Need this. Need a bit here to load the value. If you put the value here, you should load the value into the counter. If I put 5, or I need 4 bottles to be counting with this at each sequence. Once I input the value, I should load it here. So I want to use this bit to be loading whatever value that is inputted here. Okay, so in that case, we can say it's going to be value loader. Let's call it a value loader. Okay. Um, all right, then we should also reset. We should also reset here by putting a stop process. You know, for us to reset the operation of this counter, we should have a bit here that will reset. This arrow stands for reset, to reset the operation here. You can do that. Now, okay, so we are done. Now, if I want to load this, I will manually, once I put, for example, let me say I put 8 bottles, or let me say 10. I put 10. Okay, I put 10, but it's going to be C hash 10. Supposing I put 10 here, this value is not going to be recognized by the counter until I load it into the counter. So how do I load? Is by clicking this value loader to load this the first time. Then subsequent time, you won't be needing the loading. The system will have to load it by itself. All you need is for the sensor here to be clicking, for the sensor to for this sensor to be sensing the number of item coming and be counting. Once this sensor count each